Good afternoon, Internet. I am Matt Buyak, and in this video, we'll take another look at the 26th problem from the Project Euler problem archive. Now, in the last video, we solved this problem using C++ and programming. In this video, we're going to solve it using analysis alone. Now, you may have noticed it's been a little while since I uploaded the original video. It turns out that this problem was a little bit more formidable than I anticipated. As such, I expect this to be a fairly lengthy video, but I do hope you'll stick with it. I found the eventual solution to be quite satisfying, and I think that you may as well. So let's take a look at this problem. This problem asks a question about the decimal expansion of reciprocals of natural numbers. We know that any rational number will have a decimal expansion that eventually repeats in a cycle. And this problem asks us to find the natural number d less than 1,000, which corresponds to the longest such cycle. So let's get into it. Now, as I mentioned, I expect this to be a fairly lengthy video. And so I want to give you kind of a roadmap for how we're going to go about tackling this problem. So the first part is going to be a recap of the algorithm that we developed last time, and a look at how we can translate that algorithm into an equation that's maybe more amenable to analysis. In the second section, I'll introduce some standard concepts from number theory and take a look at how those apply to our problem. In section 3, we'll try to narrow down our search space from all natural numbers less than 1,000 to just a few particular candidates that we think might be our answer. And then in the fourth section, we'll inspect each of those candidates and see which is in fact our answer. Okay, so part 1, the setup. So as I mentioned, we developed this algorithm in the previous video for calculating the decimal expansion of rational numbers. And if you want to see all the details of that, I would recommend checking out that video. But I'm just going to summarize it briefly here. Basically, we're going to start with a remainder of 1, which corresponds to our reciprocal. And we're going to repeatedly multiply by 10 and find the remainder after dividing by d, our denominator, to get this sequence of remainders here. And eventually, we're going to see some remainder repeat. And that will indicate the end of our cycle. Now, in this case, it turns out that the repeated remainder was also our starting remainder, that is 1. But that's not necessarily the case. It's possible for some other number to be our remainder. Okay, so let's see if we can translate the idea of this algorithm into an equation. So let's say let r be the repeated remainder for denominator d. So what we're doing in this algorithm, just to reiterate, is repeatedly multiplying by 10 and taking the remainder after dividing by d. And so this allows us to write this key equation, which is going to be r times 10 to the k is congruent to r mod d for some positive integer k. Now, if you're not familiar with modular arithmetic, this is just saying that if we take r times 10 to the k and divide by d and take the remainder, that we get back our original remainder r. I also want to just say important note. We're interested in the smallest solution to this equation. You could imagine, for example, with our example up here, the decimal expansion of 1/7 is 0.142857. But if we consider that cycle repeated twice as a single cycle, that is 0.142857, 142857, that's also a solution to our equation. But that's not really what we're looking for. We're only interested in the first repetition. So I just want to be aware of that. Okay, so looking at our key equation here, you might guess that we should be able to divide both sides by r. But it turns out that that's not actually a valid conclusion. That is, we can't conclude, at least not directly, that 10 to the k is congruent to 1 mod d. And your counter example is just going to be 2 times 10 cubed is congruent to 2 mod 6. But 10 cubed is congruent to 4 mod 6, not 1. So where did we go wrong? Why was our intuition for this equation not correct? And the reason is that this isn't standard arithmetic. This is modular arithmetic. And so it behaves a little bit differently than if this were a proper equality. And so I'll just say, what our equation actually means. And this is going to be that d divides r times 10 to the k minus r, or equivalently, that d divides r times 10 to the k minus 1. And this is true of any congruence like this. If you have a to the b congruent, a congruent to b mod d, that's the same as saying that d divides a minus b. And so from this statement here, you might be starting to get a little bit of intuition around why our previous assumption was not correct. But let's dig into the details a little bit. We'll say, note that if 10 to the k is congruent to 1 mod d, this is equivalent to d divides 10 to the k minus 1. And so you'll notice that if our intuition were correct, that our statement here that we've derived would also be true, but the reverse is not necessarily the case. So let's look at the situations where this fails, where we can't conclude d divides 10 to the k minus 1 from d divides r times 10 to the k minus 1. So we'll say, case 1, and that's going to be r is equal to 0. And this makes sense. If r is equal to 0, it doesn't matter what the value of 10 to the k minus 1 is. This is going to have the value of 0, this whole right-hand side. And so d is always going to divide 0. It doesn't matter what the value of d is. You'll notice also that we're not particularly concerned with the case where r is equal to 0, because that means that the decimal expansion ends in a cycle which is only length 1. So we'll just say this case has cycle length 1 and is just 0 repeated forever. And since we already have an example with a longer cycle, that is 1/7, has a cycle length of 6, we don't need to be worried about this case because it's a cycle length of 1. But we do need to be careful to avoid this case. So how do we do that? Well, in order for the remainder to be 0 at some point, you'll recall we're starting with 1, and we're repeatedly multiplying by 10, and then dividing by d. So in order for r equals 0, we have d divides 10 to the j for some positive integer j. But the only way this is true is if d has only prime divisors 2 and 5. Or stated another way, if d has any prime divisor other than 2 or 5, r is greater than 0. Great. Okay, so now let's look at case number 2. And this is going to be r greater than 0, but greatest common denominator, divisor of r and d greater than 1. So why did I add this extra condition here on the end? Well, going back to our statement up here, you'll see that if r and d are relatively prime, that means that d must divide the right-hand side. And that just leads to our intuition over here, which is actually the statement that we're kind of working toward. And so the only failure case remaining is going to be when r and d are not relatively prime. So let's consider that case. So we'll say, recall that d divides r times 10 to the k minus 1. This means, first let's say let g equal GCD of r and d. That's just going to make our analysis a little bit simpler here. Okay, so that's going to mean that d over g divides r over g times 10 to the k minus 1. You can think of this just as a fraction, with the denominator and numerator, and you're just dividing out the common divisor from the top and bottom, essentially, to get this statement here. But now, since d over g and r over g are relatively prime, we know that d over g divides 10 to the k minus 1. Or equivalently, 10 to the k is congruent to 1 mod d over g. Okay, so why is this important? Well, this should look rather familiar, since it's essentially the equation that we're trying to get to, but with a different denominator. And in fact, a smaller denominator than what we started with. And so this is going to give us our next key result, which is if GCD of r and d is greater than 1, there exists some smaller denominator with the same cycle length. And we'll just say, in particular, the rational number 1 over d over g has the same cycle length. Okay, so this allows us to make the sort of key conclusion from this section. So we'll say key result. The solution to our problem corresponds to a solution to 10 to the k congruent to 1 mod d. And I'll just note, as we already noted previously, the smallest positive such solution, in case we've forgotten. Okay, so that's going to wrap up section 1. Now let's go on to part 2, the theory. Okay, so let me give an important definition that's going to allow us to restate our problem in simpler terms. So we'll say definition. The smallest solution, say smallest positive solution to b to the k congruent to 1 mod d is called the order of b. That is the smallest value, positive value of k, which solves this congruence. That's the order of b mod d. And so this allows us to, we'll say problem restatement. Find the natural number d less than 1,000 such that the order of 10 mod d is maximized. And as we've already seen, there are some values of d where this doesn't, where the order of 10 is infinite. So I sort of implied in this is that the order of 10 is finite. Okay. So now, first key theorem from number theory. So we'll say theorem. If 10 to the k is congruent to 1 mod d, then ord 10 divides k. And this is actually pretty easy to prove, and so I will do so now. So we'll just say let k equals s times ord 10 plus t. A quick note about notation. Anytime I don't mention a specific modulus, ord 10 mod d, it's mod d. I'm just going to leave that as implied unless I state otherwise. Okay, so here we're just dividing k by ord 10, and we're getting our quotient here and a remainder here. We'll just note t less than ord 10. Okay, so we know from our theorem, assumption here that 10 to the k is congruent to 1 mod d. So let's write 1 congruent to 10 to the k. And so then we can just substitute our expression for k here. So that's going to be 10 to the s times ord 10 plus t. And then by exponent rules, that's just going to be equal to 10 to the ord 10 to the s times 10 to the t. But we know that from the definition of the order of 10, that 10 to the ord 10 is just going to be equal to 1. So then we have 1 to the s times 10 to the t is just going to be equal to 10 to the t. And so you'll notice that this appears to also be a solution to our equation. That is, this is, we'll just add mod d at the end. So 10 to the t is congruent to 1 mod d. But obviously we've already assumed that t is less than ord 10, and so we know that t can't be a positive solution to this equation. It has to be equal to 0. We'll just say, because t less than ord 10, t is equal to 0. So putting this back into our equation up here, we get k is equal to s times ord 10, or that is ord 10 divides k, which is what we were trying to prove. Okay, great. So now another theorem from number theory, and this one I will not prove. I'm going to state it first, and then I'll explain what I mean by it. It may not be, it may seem a bit opaque at first statement. So I will say theorem, and this is going to be Euler's theorem. This is just going to state that if if GCD of B and D is equal to 1, and then B to the phi of D is congruent to 1 mod D. Okay, so what is this? What is this phi function? What's this theorem saying? Well, this phi function is the Euler totient function, and I'll get to defining that and talking about how to calculate that in just a moment. But even without knowing the details of that, I just want to note a quick corollary, and that is phi of D gives an upper bound on our cycle length. That is because phi of D solves our equation here for B equals 10. That means our solution K can't be greater than phi of D if it's to be the smallest solution. But there is a caveat. We need to make sure that this condition is met. So I'll say, when is it the case that GCD of BD greater than 1? Or specifically, in our case, we're concerned with 10 and D. We'll say, note, if GCD 10D is greater than 1, then 2 divides D or 5 divides D. Okay. Also, recall that D divides 10 to the K minus 1. You'll just remember that from section 1. That's That's what we're trying to find is solutions to this statement. But this means that 2 divides 10 to the k minus 1, or 5 divides 10 to the k minus 1. However, this is a contradiction, since 2 divides 10 to the k and 5 divides 10 to the k, neither 2 nor 5 can divide 10 to the k minus 1. And this gives us a key result, which is that for our solution D, the greatest common divisor of 10 and D must be 1. To be clear, obviously you can have values of D for which this is not true, but those will not correspond to our solution based on the work we've already done. Okay, this means that Euler's theorem does apply, and this phi of D up here provides us an upper bound on our cycle length. Very useful. Okay, so now what is the Euler Totient function? So we'll just say definition. Phi of D is the number of positive integers less than and relatively prime to D. For example, phi of 12 is equal to 4 because 1, 5, 7, and 11 are relatively prime to 12. Now, fortunately, we don't actually have to determine this list in order to calculate phi. Otherwise, it would be a much less useful function if we actually had to find these integers every time. So we'll just have a theorem here, which is that phi of D is going to be equal to D times the product of P minus 1 over P over the prime divisors of D. That is, we're going to evaluate this product over, with this expression, over the prime divisors of D. And again, we'll say, for example, phi of 12. You'll note that 12 is divisible by 2 and 3. Those are its only prime divisors. And so we'll say this is going to be equal to 12 times 1/2 times 2/3 is equal to 4. Much easier than having to list out these integers here. Okay, so now we have this upper bound for our cycle length. We know how to calculate it. And you might make a reasonable guess, say reasonable guess. Ord 10 might be maximized for values of D, where Ord 10 is equal to phi of D. And this actually has a name, and so we'll say definition. Yeah, so we say that if Ord B is equal to phi of D, I should clarify this is Ord B mod D. Then we say that B is a primitive root. Let me just put this in quotes. Mod D. And so translating our reasonable guess into this new language, we would say that it seems likely that, say, it seems likely that 10 is a primitive root mod D, where D is our solution. Okay. Now this is a very useful guess. Again, it's at this point still just a guess. But it turns out that only very specific integers can even have primitive roots, let alone have 10 as a primitive root. And so another theorem, and this is if D has primitive roots, it must be one of 2, 4, p to the a, or 2 times p to the a for odd prime p and positive integer a. Okay, again, I'm not going to prove this theorem. It turns out that the proof of this is actually quite lengthy, but I am going to give a shout out. If you're interested in primitive roots and number theory, check out Michael Penn's YouTube channel. So he has an entire series on primitive roots and leading up to this proof. And so I would highly recommend you check that out if that sort of thing interests you. This is where I got most of my information on this topic. Yeah, so I would definitely highly recommend that. It was also, his channel was one of the motivations for me to start my own YouTube channel. Yeah, so I'm definitely a big fan. Okay, so now we're on to part 3, narrowing the search. Okay, so at this point we've guessed that 10 is probably a primitive root mod D, and we've narrowed down what the possible values of or values of D that have primitive roots can be. But we haven't actually given strong evidence, that this is the case. So we're going to do that now. So let's suppose that 10 is not a primitive root mod D. This would mean ord 10 is less than phi of D. Also recall, we proved this earlier, that ord 10 divides phi of D. And that's because any solution to 10 to the k congruent to 1 mod D must be divisible by ord 10. Okay, so this means that we can write 2 times, let's say, therefore, 2 times ord 10 is less than or equal to phi of D, which is less than D, which is less than 1,000. you'll just note that this follows pretty clearly from the definition of phi. In particular, you'll note that if D is prime, then phi of D is D minus 1. Okay, so dividing both sides of this equation by 2, we can conclude that the order of 10 is less than or equal to 499. We have to be a little bit careful about this because since we're mixing less than and less than or equal to, D has to be less than or equal to 999, phi of D less than or equal to 998, and so ord 10 less than or equal to 499. Okay, so we have key result. Let's see. If 10 is not a primitive root of D, mod D, then the cycle length is less than 500. Okay, great. So now let's consider the case where 10 is a primitive root, but it's of the form 2 times p to the a. So you'll recall from our theorem up here, we have these different cases for numbers which can have primitive roots. We're not interested in 2 or 4. Those are divisible by 2, which we've already ruled out. And so actually, this is kind of funny. I'm realizing now that we don't need to consider. I was going to consider 2 times p to the a, but it's actually not necessary. Well, let me show you the analysis that I had prepared, and then we can ignore it because it's actually not relevant. So let's suppose suppose D is equal to 2 times p to the a. Then we would have phi of D is going to be equal to p minus 1 times p to the a minus 1, which is less than p times p to the a minus 1, which is equal to p to the a, which is equal to d over 2, which is less than 500. And so again, we can conclude that phi of D, we'll say key result. If D equals 2 times p to the a, phi of D, or rather, the cycle length is less than 500. Though, as I mentioned, we'd previously ruled out values of D divisible by 2. In any case, let's press on. Okay, so now we get to the big result of this section, which is that if our cycle length is greater than or equal to 500, D is a prime power. All right, and this seems, again, it's still possible that our cycle length is less than 500, but that's starting to seem unlikely. Again, we have our range is, numbers less than 1,000, and so it seems unlikely that we wouldn't be able to produce any cycle lengths less than or between 500 and 1,000. And we'll get some more concrete information on that in just a moment. And so, we'll say key observation. The only prime powers with exponent greater than 1 between 500 and 1000 are 961, 841, 529, 729, and 625. And we'll just note that 961 is equal to 31 squared. 841 is equal to 29 squared. 529 is equal to 23 squared. 729 is equal to 3 to the 6th. And 625 is equal to 5 to the 4th. And we'll just say note phi of 961 is equal to 930. And we'll just also note, this could be a key result, but it's pretty easy to calculate. But we'll just say note if D is prime, then phi of D equals D minus 1. I think I had mentioned this previously. And so now we'll note this key result, which is that if any prime between 931 and 1000 has 10 as a primitive root, the largest such prime is our solution. Okay, so it does seem like we're starting to narrow in on our solution. You'll note that we don't have any guarantee at this point. Let's say, we don't know how common it is for 10 to be a primitive root. But I will note, if a primitive root of D exists, there are phi of D primitive roots. And I'm not even going to bother making this a theorem because we're not really going to use it, but it does give some motivation for us to think that maybe this isn't a rare occurrence. You can try plugging in some values of D here, which are large primes close to 1000, and you'll see that it's not uncommon. I will say, also note, it is not uncommon for 1/3 to 1/2 of the values less than D to be primitive roots. And I should say integers rather than values. There we go. Let's be specific here. And so this gives us some motivation, again, that we might not have to look very long or hard to find our solution. Now, I have to confess, I'm actually rationalizing a little bit here because I already know the answer. We solved it using C++ and programming, but if I didn't know what the answer was, and I had reached this point in my analysis, I would think that it was very likely that some large prime close to 1000 would have 10 as a primitive root. And if I checked, a few possibilities and I didn't find an answer, then I would start trying to tackle it from the other angle, which is why do I not find these expected solutions? But in any case, this basically brings us to the end of section 3. So I'll just note our candidate solutions are large primes just less than 1,000. Okay, part 4, the solution. All right, so we've talked a lot about primitive roots, but I haven't really talked about how to calculate them or determine whether a number is a primitive root. Let's see. So let's take a look at the largest prime less than 1,000, and that's 997. We'll say note phi of 997 is equal to 996, since 997 is prime. And that's going to be equal to 2 squared times 3 times 83. This will be important in just a moment. Okay, so again, actually we'll just say key observation. The easiest way to prove that 10 isn't a primitive root is to actually let me state it this way. We'll say theorem. And I think I'll state the theorem, and then I'll explain why it's true. And so we'll say 10 is not a primitive root of d if 10 to the phi of d over p is congruent to 1 mod d for some prime divisor of d, p. Okay, so why is this true? I'm not going to give an actual proof of this, but the reason is that because any solution to this equation is divisible by the order of 10, and 10 is a primitive root of mod d only if ord 10 is equal to phi of d. If this equation is true, that means that there is some solution to this equation that is less than phi of d, which means that 10 cannot be a primitive root. And the reason why we're checking these values in particular is that because ord 10 has to divide any solution to this equation, in particular, it has to divide one of these values. If ord 10 is not equal to phi of d. This means we can show 10 is not a primitive root of 997 by testing, and it's going to be 10, let's see here, 10 to the 498, 10 to the 332, and 10 to the 12th mod d. And you'll note that these are just 996 divided by 2, 3, and 83 respectively. Okay, so how do we calculate these values? Like 10 to the 12th, oh, and I should say actually 997. We're not, we've specified D at this point. So 10 to the 12th is easy to calculate. Any calculator is probably going to be able to handle that. We could even do the math by hand if we wanted to, and it would be fine. But something like 10 to the 498, that's going to be much more difficult to calculate by hand. And so I'm going to show you a technique for doing that. Now, I'm only going to use this technique for the first candidate, 997. Spoiler alert, 997 is not our solution. So I'm going to show you how to do this using the long way. And then I'm going to use the calculator because the Windows 10 calculator is magic. And rather than switching over to floating point for large numbers, it actually has big integer support. And so we can just calculate these values directly. Very nice. But let me show you how you would do this if you were solving it with pencil and paper. Okay, so the idea is that we're going to repeatedly square our remainder in order to build up this dictionary of powers of 10 mod 997. And so we'll say 10 to the first, that's obviously 10. And these are all, I'll just put up at the top, all mod 997. Okay, square that, and obviously we get 100. Square that, and we get, let's see here, mod 997, 30. 10 to the 8th is going to be 900. 10 to the 16th. And I am using the calculator's mod function here, but I think you can see that this is all arithmetic that you could do on paper if you had to, in a reasonable amount of time. And if you haven't seen this technique before, it might be unclear what I'm doing exactly or why I'm doing this. I will explain in just one moment. As you can see, I'm repeatedly squaring both sides of our equation. Let's see here. We'll leave this to the second, mod 997, 888. And already you can see we've got this value 10 to the 64th congruent to 888 mod 997. And this is probably not a value we could have calculated by hand, doing it the naive way. If we, writing out a 1 followed by 64 zeros and then doing the long division, probably not going to happen. Certainly would take much longer than this technique. Okay, so let's square that. Mod 997 gives us 914. What was that again? 914. And finally, 10 to the 256 is 907. Okay. So how does this help? Well, you'll recall from our observation up here, we need to check each of these values to see if they're congruent to 1 mod 997. And so first we'll try, we'll say, note 10 to the 498 is going to be equal to 10 to the 256 times, let's see here, 498 minus 256 minus 128 minus 64. Minus 32. I believe that's what we had remaining. Yes, 18. Okay, so I hope you can see why this is true. And then we'll just pull each of these values from our dictionary that we built up here. So 10 to the 256 is going to be 907. It's going to be times 914 times 888 times 666 times 436 times 100. Let me just double check my work here. So we have 907, 914, 888, 666, 436, and then 10 squared. Okay. So we'll do 907 times 914 mod 997 times 888 mod 997 times 666 mod 997 times 436 mod 997 times 100 mod 997 is equal to 1. Ta-da! So we'll just say equals 1. Okay, so that's the long way of calculating this. Very tedious, very error-prone, but you can see how it could be done by hand. And in fact, you'll note that I was even doing, mod 997 after each step in this multiplication. With a calculator, I could just multiply all of those together. But if you were doing this by hand, you would probably want to multiply two of these together, do the mod, and then repeat the process here. With the magic of technology, we can just do 10 to the 498 mod 997. Boom, done. Way easier. Now I'll note that not all calculators will behave this way. Many of them switch into floating point for large numbers, and then this won't work. But fortunately, I have a calculator where this does work, and so this is how we're going to do the rest of our candidates. Okay, so now we need to do 10 to the 332. Actually, no. My mistake. We've already shown that 10 is not a primitive root mod 997. So we can move on to, now let's consider d equals 991. Note, phi of 991 is equal to 990, which is equal to, what is that? 3 squared times 5. 2, there we go, times 11. Okay, so we'll need to test 10 to the 495, 10 to the 330, 10 to the 198, and 10 to the 90th, mod 991. And I guess I should just add up here. Key result, 10 is not a primitive root mod 997. Okay, so let's do it. 10 to the 495 mod 991. Oh, well, that was easy. Key result. 10 is not a primitive root, mod 991. Let's consider d equals 983. And we'll say note phi of 983 is equal to 982, which is equal to 2 times 491. So we'll need to test 10 squared and 10 to the 491. Oh, mod 983. Okay, so obviously 10 squared is 100, so we don't have to check that. So 10 to the 491 mod 983 is not 1, it's 982. And you'll notice that if we then square this and do mod 983, then we do get 1 as expected, because 10 to the phi is congruent to 1 mod 983. But the fact that neither 10 squared nor 10 to the 491 was congruent to 1 mod 983, we have our key result and our solution. 10 is a primitive root mod 983, and therefore our solution. Actually, let's say final result. Okay, so now we can go back to the archive and check our answer and see that it is indeed 983. So if you managed to make it all the way through that video, congratulations to you. Thank you for joining me. I enjoyed preparing this video very much, and I hope you enjoyed it as well. In the next video, we will tackle the next problem in the archive, problem number 27.